Hello, and welcome back to a video series on MAT 1033 Intermediate Algebra. My name is Sean Perry. This is video number 17, Problem Solving with Linear Systems. So this section is going to be on word problems and how we attack word problems that essentially boil down to solving linear systems of equations. The trickiest part is going to be writing down what the system is. From there, you'll solve using the techniques from the last two videos. As with any word problem, each fact that we're given needs to be extracted and encoded as an equation. That's what lets us use math to tackle these otherwise linguistic problems. Now, unlike previous word problems, where sometimes all you really needed to extract is a single equation, now we need to think of all the different facts and take them together into several equations and then solve that system. There may be several unknowns that you need to find, several answers that they're looking for, or there might be intermediate answers, which are stepping stones on the way to getting some single final answer. It'll vary from problem to problem. Now, I just want to point out, this is the real task in mathematics. Doing the math after it's set up is one thing. It's a very important and useful skill. But setting up those equations, figuring out how to describe reality using mathematics, that's the work. That's the work that you're being asked to do here. And that's what makes math useful in general. One reason that you might think to yourself, well, math doesn't seem to be applicable. I learn all of these silly facts, but they never seem to have any ground in real life, is because grounding them in real life is a skill. And if you eschew practicing that skill, it doesn't matter how good you get at solving the equations, you'll never see the connection to real life. So this is a really good opportunity to dig down and try to develop that skill. Try to be able to, for each one of the problems we're about to look at, think about how you would assign an equation to the facts being presented. So let's start with a simple one in the sense that I am just going to be asking about two numbers, right? That's the facts that are given. So it says find two numbers with a sum of 36 and a difference of 10. So I want you to think about how you might write down those facts into equation form. So first think about the things that we're interested in. We are asked to find two numbers. It's worth giving them names right off the bat. Let's call them X and Y. Perfectly good names for a variable. You could choose A and B, alpha and beta, whatever you like. Now we have to think about what facts relate those numbers together. We know their sum is 36, and we know their difference is 10. How do we write those down as equations? Well, the sum of those two numbers is given as 36, so we add them. Sum means add, difference is subtraction. The difference of those two numbers is 10. So here I've encoded those two as facts. Notice that there are two unknowns and two equations. So now we want to go ahead and solve this system. It's already in the form where we can use Gaussian elimination. There's a plus y and a minus y. So if I add these two together, I get 2x's is equal to 46. Divide by 2, we get that x must be equal to 23. And if we take that back to the original equation, we can see that we have 23 minus y must be 10. Let's just add the y to the other side, subtract the 10 on over. So 23 minus 10 must be y, and that means that y is equal to 13. So in conclusion, we find that x is 23 and y is 13. All right, now let's look at problem 2. Problem 2 asks us to compare two companies' phone plans, which is going to be the less expensive, a company which charges $65 a month for $5 additional per gigabyte of data, or another company that charges $50 per month, but then they charge you $10 per gigabyte of data. Now, how much data would you have to use to make one company a better choice over the other? This is a very normal modern problem. The main idea here is that we can see that one company is going to be more expensive than the other if I don't use any data. Yeah, like that's going to happen. But it depends on how many gigs I'm going to use. If I keep adding $10, $10, $10, $10, eventually that's going to be more than if I just add $5 per gig, even though this price starts out a little bit more, right? Like if I have 10 gigs and that's another $100, that's $150. Well, this is only $115, 50 plus 65. So we right off the bat can do a little bit of pre-math on this problem. We can see that one of them starts out more expensive for a small number of gigs, but the other one becomes more expensive for a large number of gigs. And so now we can kind of attend to this question a little more seriously. How many gigs, something between 0 and 10 definitely, would I need to use, I don't know where company C came from, for company A to be a better choice? So the first thing we need to do is identify what we're interested in. We're interested in data use, how much data is used, and the cost for two companies. Now, let's assign variable names to those quantities. Let's say the amount of data is D, right? What I'm doing here, this assigning names, naming the things is very important. This is how you start to write them into equation form. First, you need to pick out what the nouns are. What are the subjects? What are the things in the problem? There's data amount in gigs. There is company A's cost, and there's company B's cost. Let's call cost C, and we'll call cost for A, company A, CA, right? You should use natural variable names if you want to kind of keep track of those things. We could say X, Y, and Z here, right? But then, it might be harder to remember what each one means. Here we know D is for data, CA is cost of company A, and CB is cost of company B. But what do we know? What facts we were given? Well, we were given a way to figure out cost given the data used for each company. So let's write those equations down. Now, it was $5 per gig plus $65 fixed for company A. So if you want the total cost, and you know it's $5 per gigabyte, and D measures how many gigabytes, then 5 times the number of gigabytes gives you the cost, the additional cost for getting that many gigabytes. Likewise, for company B, it's $10 per gigabyte. So 10 times the number of gigabytes gives me the total cost of D gigabytes, plus $50 fixed for each month. And what do we want to solve for? Well, we want to solve for D. And we know that company A is going to start out as a higher price for, say, D equals 0, and company B is going to start out as a lower price. One thing we could do to model this problem is use technology. One important thing about visualizing your models is to choose a good scale. We can see that all the business is happening here between 0 and 10. So on Desmos, you can go into the settings and you can change your x-axis. Let's only look between 0 and 10. So here's company company A. It starts out higher. It starts out with 65 a month. And company B, which starts out at 50. Now, as you spend more, company B increases the amount of total money at a faster rate and will eventually be greater than company A. And where does that seem to happen? Well, we can honestly just click on the intersection here, and it happens at x is equal to 3. Remember, x is our stand-in for D here, which is the number of gigabytes of data that we are using. So here we've basically solved it. They both cost $80 a month if you spend 3 gigabytes. And if you get more gigabytes, then company B will be more expensive and A will be less expensive. Now, that gave us not just some intuition, but the answer. But it also, I think, gave us some good intuition. How might we have done this with algebra? So what we would have to note is that as D gets bigger, eventually A is going to be smaller than B. But at some point, they're going to be equal to each other. And at that crossover point, that's where we're going to want to solve. Because ever after that, company B is going to be the larger of the two. So we can set them equal to each other, right? And solve for D. And here's me doing that. In doing so, I would find D is equal to 3. So if you use more than 3 gigabytes, you should go with company A. All right, let's keep going with problem number 3. Problem number 3 says the following. Say a river floats at a constant rate, and a boat is traveling along that river at a constant speed. How fast are each going, if it takes 2 hours to go 15 miles upstream and 1 hour to go 15 miles downstream. If you're going upstream, you're going against the current of the river. And if you're going downstream, you're going with the current of the river. So what do we really want to know here? Speed of the river current and the speed of the boat. And let's give them names. Let's say V sub r is going to be the velocity of the river, and I'll say the velocity of the river, the velocity of the boat. And now, what do we know about them? We want to encode that fact about upstream and downstream movement. It says that it takes 2 hours to go 15 miles when they're moving against each other, and 1 hour only to go those 15 miles when they're moving with each other. So when they sort of enforce each other, when you're not fighting the stream, when you're going downstream, it only takes you an hour. But if you have to fight against the current, it takes 2 hours. So can we figure out just with that, what is the speed of each one? In order to do that, we really have to get a speed out of this. So we have miles and we have hours, but that's not exactly speed. It's important to have a few key equations. Distance is equal to rate times time. This is one they're going to hit you with over and over and over again. It's important to your actual life. It's what a rate means. You need to memorize this, right? You want to know the distance that you travel. It's the rate times the time. 15 miles took 2 hours. In other words, that rate, divide the 2 hours over, is 15 over 2, or 7.5 miles per hour. So that's their total combined rate when the boat and the river are working against each other, right? We get that by dividing the number of miles by how many hours it took to go those miles. Now, what about the rate when they're going with each other? Well, that's going to be 15 miles, the rate that they're going with each other, RW, times 1 hour. Okay, so dividing by 1, but changing the units to miles per hour, the rate that they're going with each other is 15 miles per hour. And that makes sense. It took twice as long in total to do the same trip when they were going against each other. So the rate, the total rate, was half that they were going when they were going with each other. So just to summarize where we're at so far, the rate when they were moving against each other is 15 over 2, or 7.5 miles per hour. And when they're moving with each other, when the river and the boat are helping each other, it's 15 miles per hour total. Now, what we have to figure out is what to do with this with and against concept, right? How does the river traveling along the same direction as the boat, or traveling the opposite direction as the boat, form up into an equation? When you go with the flow of the river, it adds to your total speed. And likewise, if you go against the flow of the river, that's shifting you back. It's subtracting from your total speed. So what we have is the following equations. Here is the facts given turned into equations. When I'm going against the river, my rate is going to be the rate of the boat minus the rate of the river, because the rate of the river is moving opposite the boat. But when they're traveling downstream, when they're going together, the boat and the river go along with each other. And the boat goes some, and the river pushes it a little bit more in the same direction. And that's going to be what we call the rate with. Now, we figured out, using the information given, these two amounts, the total rate when they were traveling against each other, and the total rate when they were traveling with each other. The total rate when they were traveling with each other was 15, and the total rate when they were traveling against each other was half that. So if I add these together, what I find is twice the velocity of the boat. 15 over 2 is 15 is 30 over 2. So adding 15 and 30, we get 45 over 2. And then dividing off my 2, I get 45 over 4. So we found it, the rate of the boat. The rate of the boat is 45 over 4, or just maybe like 11.25 miles per hour. And what about the rate of the river? Well, let's go back to the this equation here, right? Velocity of the boat plus velocity of the river is 15. Well, 45 over 4 plus some amount is 15. We subtract that over. 15 is 60 over 4. And so taking the difference with 45, we get 15 over 4. And that's about what? 3.75, right? So the river is going at about 3.75 miles per hour, and the boat is traveling at 11.25 miles per hour. All right, so let's look at problem 4. This is a dilution problem. It says solution A is 50% bleach. Solution B is 10% bleach. How much solution A do we have to add to solution B, to 1 liter of solution B, in order to get it to be 20% strength? In other words, 20% bleach. A is very concentrated. If we keep adding, if we only add a little bit, it's still going to be only about 10% bleach. But if we add a lot of it, it's going to be nearly 50% bleach. So somewhere in there is going to be a point at which it passes 20% bleach. How do we find that point if we were trying to get this to be exactly 20% bleach? Well, first of all, let's sort of draw a picture of what we have going on for the two solutions. Number one, we have solution A, which is 50% bleach. So let's shade it 50% to be like, yeah, that's all bleach. And then B, we have only a tiny sliver of it, 10% is bleach. And now if I took all of A, well, it depends on how much A we have. We know how much B we have. We don't know how much A we have. And we don't know what adding all of it would do. We know that when we add some of it, though, some of what we add is bleach, and the rest is buffer liquid. So how much are we going to add? This is the first thing we want to name. I want to name how much we're going to add, because that's the question, right? The question was, the thing we're looking for, how much of this solution A should you add? So let's call that X. Now, the important thing is, how much of that is bleach? Well, A is 50% bleach, so we would say 0.5 times X. That's how much bleach is in the amount of solution that we just added. If we add X amount, 50% of that, or 0.5 of that, is going to be bleach. Now, how much stuff do we have, right? Like, visualize this. You've just added some amount of A into B. How much total do you now have? What is the total amount of solution A plus your liter of solution B? Well, you have 1 liter of solution B, and you're adding X liters of solution A to that. So in total, you're going to have 1 plus X in volume. But how much of that is bleach? So of that 1 liter, only 10% of it is bleach. So 0.1 times 1, that's 0.1 of it is bleach originally. And then we're adding 0.5, or half the amount of the volume added, is going to be bleach. Now, we've just found an expression, these are two equations, for the total amount of something and the amount of that is bleach. Now, if you want to know when is that 20%, we need to make the ratio in question and then set that equal to the amount we have. So, for example, I have the total new amount of bleach. That's 0.1 times 1 liter, the amount of bleach in solution A, plus 0.5 times X. That's the amount of bleach that we just added. So this numerator is the total amount of bleach. If you want concentration, it's the total amount divided by the volume. So that's 1 plus X, the total amount that we added. So now we know at some point that's going to be equal to 20%. All I need to do here is solve for X. Now, to solve this for X, we need to get this off the bottom here, so we multiply it to the other side. Boom. Now it's a linear equation. We distribute the 0.2, and we solve. Subtracting 0.1 from both sides, subtracting 0.2x from both sides, I get that 0.3x is equal to 0.1, and dividing away my 0.3, I get a third. 0.1 over 0.3 is the same as 1 over 3. So 1/3 of a liter. I need to add 1/3 of a liter to this, and that will give me a 20% concentration. So one last thing is I'd like you to copy this down as critical notes. Some sort of background information to all the problems that we looked at today is this usage of the word per. Now, per in mathematical terms means division. When you say miles per hour, you're talking about the total number of miles divided by the total number of hours. And if you can remember that, you can actually remember the distance equals rate times time equation, because rate is miles per hour, or distance per time, is distance divided by time. And multiplying time over to the other side, we get that distance is equal to rate times time. So sort of the meaning of the word per is baked into that equation of distance equals rate times time. Another place that it popped up was in cost per unit. We talked about, dollars per gigabyte in one of the problems. Well, dollars per gigabyte, or cost per unit of something, is the total cost divided by the number of units. And rearranging this, if what you really wanted was cost, you could multiply by that and get something very similar to this equation, where the total number of units times the cost per unit would give you the cost. So this is just another application of the idea of per being in terms of division, right? And one last thing is per cent, right? There's even a per thing in here, but per cent is in terms of hundredths, because 100% is the total amount of something, right? It's all done in terms of 100 or in terms of hundredths, and hundredths is centi in the Latin, I believe. And so you still have division going on in percents. Usually it's a part or an amount that you're interested in comparing to some total. So when we deal with percents, another thing that sort of formed some background information here about how to do any of these problems was that would be a part or an amount that we were interested in comparing to some total, and we're comparing them through division. So that we get, if, for example, we had 100% of something, or the total divided by itself, right, that would be the number 1, which is 100 hundredths. And that's why, percents have to do with hundredths like that. 1 is 100%. This is also having to do with when we talk about, 23% of something, right? That's the decimal 23 hundredths. So there is where the cent comes from in percent. And where does the per come from? It comes from this division. So I think all of that's pretty necessary. They assume that you guys know this kind of stuff when you're doing these problems. So I wanted to make sure that it was in your critical notes. Okay. I hope this has been somewhat helpful. I tried to give you guys my my take on how I would solve these kind of word problems, the kinds of thought processes that go through my head while I'm trying to assign equations to facts. Thank you for your patience. Good luck with your studies, and I will see you in the next video.